Student. Today I'll give a small talk on classical mechanics. Look, it is a very vast subject on classical mechanics. I'm telling you a few drops of it because different teachers, different person, different textbook, they give different versions, right? Okay, here just I'm giving a small introduction. Now, there is what is the mechanics? Suppose a body is here, an object, it is at rest. Now the body begins to move from one point to other point. From here to here is shifted. Why it is shifted? Because some force is acting on that. Therefore, there is a motion of the body because of the force. Therefore, mechanics is the study of motion. That means mechanics, when I say mechanics is the study of motion of body, movement of the body, and what causes this motion, right? That means this detailed study is done by who is the person? Newton. For every body or every object, Newton's law, there are three laws. What are the three laws? Every body remain in a state of rest. If it is rest, it will be rest. If it is moving, it keep moving. A moving body coming to the rest, or a body which is rest to start moving, that means you are applying a force. Therefore, how to define a force? Force, that one causes the change. That is inability to change its position, is called inertia. What is called inertia? Inertia means, what is the inertia of the body? It is rest. Or what is the inertia of the body? Movement. Yeah, inertia changes means what? Body which is at rest changes or begins to move, or a body is already moving, it stops or increases the velocity or changes the direction, and so on. All that. There are force causes all these things. Right? Therefore, Newton law was quite accurate for explanation of the experimental observation. Therefore, whatever experimental observation, whatever this means, Newton's law is very accurate. Exactly you can explain. Now, because here the velocity is what? Very low, that means low speed, right? If the velocity is equal to velocity of light, is it applicable? That was the question, right? Therefore, when you apply the same law, all these laws, Newton's law, if applied to the body, suppose a body like an electron, proton, neutron, or any body which is moving with the velocity of light, high velocity, you'll get a lot of error. You started getting error. Therefore, Newton's law is applicable only for a body which are moving with less speed. If the object with speed comparable to the speed of light, the theory, it gives lot of error. Therefore, another hero, see now Newton is one hero. Another hero, what is that? Einstein. Then Einstein, he did the theory. Three laws are there, right? Notice the first law, yes, introduced the momentum. What is it? Momentum, calls out momentum, mass into velocity. Then action equal to reaction, all this. Three law, But next, Einstein, he's applied relativistic mechanics. Relativistic mechanics, he introduced. There is Einstein relativistic mechanics. Einstein relativistic mechanics. If he has applied Newton mechanics, see, in this case, Newton mechanics became a special case. It is one of the special case. Okay, that is at low speed only Newton mechanics. High speed, Einstein relativistic mechanics. Therefore, Newton mechanics became a special case of the lower speed of Einstein theory. Now, this is a second hero, the first hero. Now, third hero is what? Who is the person? Maxwell. Maxwell's, he introduced that electromagnetic theory. What is electromagnetic theory? Suppose a charge, a moving, electrostatic, you have studied electrostatic. A charge at rest, it has electric field. When a charge start moving, what will happen? It will give electric field as well as magnetic field. Therefore, he could successfully explain the motion of charged body. Right? How when charge moves, what happens? How the current produces, electric current produces, and what is electric field, how it varies, magnetic field, how electric field and magnetic field are accompanying, and all the things, that interaction. Now, here, our third hero is Maxwell. He successfully described the motion of charged particle and their interaction with electric and magnetic field. It's interaction of electric and magnetic field. Next, the statistical thermodynamics and all, right? Like macro particles. There are a lot of particles are there. When lot of particles, macro particles, when a lot of particles are dealing, see, this is all our one body system. The statistical thermodynamics describe macroscopic particles and their thermodynamical properties. And all these things, from 17th century to 19th century, all this development took place. Therefore, these are called 17th to 19th century is what? Classical era, you can call classical theory. Theories of classical physics explain almost all scientific results. You take any scientific result, this time from 17th to 19th, whatever the observation at that time, it could explain Newton's law and Maxwell electromagnetic theory. All these things could explain. Therefore, theories of classical physics explain almost all scientific results of those times. And I think everybody was satisfied with Newton's law. The problem started there. Therefore, we call this called classical physics, 17th to 19th century. Right? Here in classical physics, one thing is very, very important. In classical physics, there are two entities. Matter, next, energy. Right? You got in classical physics, matter and energy. They are not same. Here, in classical physics, matter and energy or field, you can call it. Energy or field are treated as independent entities. Matter and fields, electric field and magnetic fields, and all the things are treated as different entities. And another thing also, there are assumptions. In classical physics, what are the assumptions? All macro particles, not micro particle. Macro particles, big particles. For the even atom or molecules, right? Classical physics only they applied, not inside the atom. Okay, approximately, right? And in everybody, what we observe, even in the universe, they are called macro particles, moves and interact according how they are interacting, according to Newton's law. right? Now, because interaction next, they can be described with a different path. The particle moving in a different path, it has a particular position and it has a momentum. Position means what? X, Y, Z. You can exactly it can be localized. It can be localized entirely at one particular position. It has a different place and momentum, or position and momentum at a given time. We can exactly locate. Even at this place, what is the energy at this time? You can calculate using Newton's law. So, example, wave, you can say wave theory, mechanical wave. If I try a mechanical wave, so mechanical wave, you can visualize. Example, water wave or sound wave. Sound wave. I can describe the sound wave in terms of what? Interaction of particles and intermediate particles. This example here, how the wave pulses we explain. In a water, you disturb the still water surface, what will happen? The water get disturbed and a wave is created. This wave, that energy is propagated from particle to particle and reach here. Propagation of energies, that is interaction of the particle through the interatomic forces also there. We use that wave concept like that only. And when we have large number of particles, quite a lot of particles are there. Quite a lot of particles. We use, what is it? Maxwell's Boltzmann statistics we were using. When we have large number of particles, we use Maxwell-Boltzmann statistics. Therefore, here, coming back to this, I forgot to tell you, right? Electromagnetic theory. Right? According to classical, see, there are electromagnetic theory things. What? Classical electromagnetic theory is there. Okay. Classical electromagnetic, remember, according to classical electromagnetic wave theory. Classical electromagnetic wave theory is relativistic electromagnetic theory is there. I'll tell you later. Okay. According to classical, remember classical electromagnetic theory. There was electromagnetic wave theory of two things. One is classical, another is relativistic. But anyway, according to classical electromagnetic theory, electromagnetic waves are generated. That means electric field and magnetic field. That means your high school loads as well as PU used to learn, no? There is a fluctuating electric field and fluctuating magnetic field. Both are mutually perpendicular to each other. B and E are vertical to direction, it is perpendicular to direction of propagation. And the velocity is what? Is equal to maximum velocity is equal to velocity of light. Therefore, this electromagnetic field or electromagnetic waves are generated by what? How it is generated? By accelerating charge. Accelerated charges. When a charge is accelerated, say example, your positive and negative, positive plate and negative plate, right? A charge is oscillating between these two, right? Like an alternate current you apply, when the charge is moving here and there, it's an accelerated, right? Due to accelerated charge, we are getting electromagnetic wave, right? Okay. Now the circle, you see, according to him, look, this is a nucleus, electrons moving around the circular orbit, a body is moving in a circular orbit, different direction, the magnitude of velocity is same, but the directions are different, therefore the charge is accelerated. Okay, according to electromagnetic theory, what? When a charge is moving, no, and it is moving, the piece, how it is moving, acceleration motion. When a charge is in accelerated motion, it must emit electromagnetic waves. That is called classical theory. In other words, this energy should be constant. Since energy should decrease, this was the question arised that time by Rutherford, other people. Okay, not Rutherford, Boson that time. And this you will learn later in some other thing. Just I'm telling you, according to this, accelerated charge produces electromagnetic wave, and this electromagnetic wave spread continuously throughout the space, right? The energy is not localized. See, its energy is not localized. It is not confined in one particular place. Suppose the energy is distributed in all directions. When electromagnetic wave comes, it will be distributed. It is not confined or localized, right, in one particular place. It is distributed all over the volume of the wave. Wherever the waves are there, the energy is equally distributed. That is the second point. First point is what? Electromagnetic waves are produced by accelerated charge. Another thing is what? The energy waves spread continuously throughout the space, and energy is not localized but is distributed over the entire volume of the waves. And third point is energy is what is not related to, it is not related to frequency, but energy is related to square of the amplitude, right? Square of the amplitude of the wave. These are the things we can talk about the classical theory. Therefore, classical theory we have started Newton's law. From the Newton's law, what is the study of motion? What causes the motion? And again, what? The speed should be very less. And when the body is moving with a higher velocity, you will get an error. Therefore, Einstein relativistic mechanics you can apply. That it was explained and that error can be removed. And Newton mechanics is a special case of Einstein relativistic mechanics. Then next comes Maxwell equations. Maxwell theory is what? Electromagnetic theory. According to that, what? Here it is any accelerated charge produces electromagnetic wave, right? And what is that? Motion of the charge particle he completely describes, and interaction of electric field he described in his own way. And then about for macro particles, when lot of particles are there, we can apply what? The statistical thermodynamic relations, and even sound waves and all you can understood in terms of interaction of the particles with subatomic particles, with what is that? How to say? Interaction with the atoms and particles, you can say, right? See, that is what? Large number of assembly of neutral particles can be described in statistical thermodynamics and their thermodynamic equilibrium. And this thermodynamic equilibrium by what? Maxwell. This is what? Not only Maxwell, Boltzmann statistics. This I am going to tell. Right? This thermodynamic equilibrium is explained in terms of Maxwell, Boltzmann statistics. Okay. Then what? From 17th to 19th century, almost whatever you observe there, what explained by the Newton's law. This is, then what is the origin of quantum theory? I'll tell you in the next video, right?